Before we download the files to our computer, we should organize our computer so that when we come back later, we can easily find the files. So somewhere on your computer, on some drive, you'll be storing these files. You want to create a parent folder. I'm calling it Ballistic Velocities. And within that parent folder, you want to organize your LabRadar files. You might organize it by load, such as 25-yard load, 50-yard load, major power factor load, minor power factor load. You might organize it by activity, such as if you're a hunter, your feral hog hunting load, or you might want to organize it by gun. So this folder will contain all my LabRadar files for all the loads that I use on this gun. And this folder would contain all the LabRadar files for all the loads that I use for gun 2 and so on. So however it makes sense to you to want to organize your computer first before we start downloading. For this video, I've created this folder just so I can put various series and shots into the folder just to make it easier to do the video. So now that we have our folders organized, let's download the files. There are two ways to download your data to your computer. You can use the USB cable that came with the computer and attach the large end to a USB port attached to your computer. In my case, I have a USB 3.0 hub, and then you attach the micro USB to the LabRadar unit. And then you turn it on, and you get a message that says USB connection detected. The device, which is the LabRadar unit, will remain locked until USB is disconnected. On the second way, you make sure your unit's powered off, and then you remove your SD card. The second way requires you to have a card reader attached to your computer. And if you do, you eject the SD card from your LabRadar unit and then insert it into the card reader. At that point, it is accessible by your computer. Once your SD card is connected to your computer, the computer is going to assign it some drive letter. Now in this case, it's assigned it K. For you, it could be a totally different letter. And it'll also assign it a name. For me, it assigned it USB drive. On that SD card, it has a parent folder called LBR. That folder is a LabRadar default, and we're not going to change it. But when we go inside that folder, I double-clicked it, you'll see the shot series, 1, 2, 3, and 4. Now, from the notes that I took in the field, and I'll do a quick screenshot of that form that I devised that I used in the field that I showed in video 2 of the series, I know that series 1 is a 50-yard load, and series 2 and 3 are 25-yard loads, and series 4 is not a completed series yet. So I'm not going to copy that one to the hard drive. This file is used by LabRadar. We're not going to copy it. We're going to leave it alone. On the hard drive, I know that series 1 is a 50-yard load, so I want to click and drag it to there. I know that series 2 and 3 are 25-yard loads, so I'm going to click and drag it there. Then I'm going to go to my hard drive, and I'm going to rename this. Now the reason I'm going to rename it is once you copy series over and you put the SD card back into the LabRadar unit, if you go through and delete those series, when you create the next series, it's going to start with series 1. So if you try to copy it back to the same folder, your operating system is going to tell you, do you want to replace what's on your hard drive? So per my notes, I know when I did this one, and that's just my convention. You may name it something totally different, but the point is I want to make sure that the name of this series folder is unique so I don't accidentally overwrite it at some point in the future. So I've got them renamed, and for the purposes of this video, I also copied all 3 of them down to this YouTube folder where we're going to be using them for the rest of this video. And if you want to delete the series that you've copied to the hard drive off the SD card, I do not suggest going to the SD card and deleting it in your operating system. I actually delete the series in the LabRadar unit itself. And now that we finished copying, what I do is I highlight some folder on my hard drive, I right-click the SD card, and I clicked eject. You can see that the SD card is no longer there. So at this point, we're going to go into the YouTube folder and start taking a deep dive into the data. So now we're going to take a look at the data, and we're going to go into Series 1. And when you open it up, you'll find 3 things. You'll find another folder. This contains all the tracking information, all the velocities it picked up for each shot in that series. It then has a CSV file. This contains the series information, and then it has a LabRadar proprietary file that we really don't need to worry about. Now, I have intentionally modified my computer, so it's going to open up the CSV file in the wrong application. I did that on purpose, so if it does it to you, you can see how to fix it. Ideally, when you double-click this, it will open up in your spreadsheet program, which for me is Microsoft Excel. Double-click it, and what it actually opens up in is a text editor known as Notepad. So I'm going to go ahead and close it, and now I'm going to right-click. And to fix it, I'm going to pick up Open With. Don't pick Excel because then I only fixed it for this one time. Go down and choose another app. Click Excel and then check this box. Always use this app, Excel, to open CSV files. And now it opens up. Okay, I'm going to widen column A a little bit, make it easier to read. I'm going to widen the date column. So when you look at it, and I'll move it up some, you'll see that the workbook only has one worksheet in it. And let's take a look at what's in column B. Here will be your LabRadar unit's serial number. This is the series number. This is the number of shots. This is your legend of units of measure. All velocities in this workbook are going to be in feet per second. All distances are in yards. Kinetic energy is in foot-pounds, and the weight is in grains. And these columns represent the velocities at given distances. V0 is a distance that the LabRadar unit always gives you. It's an approximation of muzzle velocity. The next 5 are the ones you specify in preferences. So this is DX1, 2, 3, 4, and 5. The 20 represents my DX1 was 20 yards. My DX2 is 25 yards. DX3 is 40 yards, 50 yards, 52 yards. And all these numbers are in feet per second. These are the shot number. This is my first shot, my second shot, my third shot, and so on. These are the statistics just for this column. So for all of these 30 shots, the average was this, the highest velocity was this, the lowest velocity was this, the extreme spread, and the standard deviation. Again, these numbers are only for V0 for all 30 shots. I'm just going to go ahead and clear these out. I already know it's in feet per second. It tells me up here. And I'm going to be using this column because I want to get these statistics in these other columns. Over here is your kinetic energy. These numbers here are not in joules, they are in foot-pounds, as our legend told us. This column is power factor. As a reminder, the LabRadar calculates power factor based on the distance you set in DX1, which for me was 20 yards. So this is the power factor for these shots at 20 yards. The sport I compete in doesn't use power factor, but for the purposes of this video, I did do a series where I set the DX1 to 10 feet. And the reason I chose 10 feet is because the USPSA rulebook for 2019 in Appendix C2 states that 10 feet is a minimum distance. And we'll take a look at that later in this video. Here's the projectile weight and here's the date. So in order to get the stats over here, you might think you could just copy this, drag this over, and get it, but that's not going to work because these are not formulas. These are the results of the formulas that were executed in the LabRadar unit. So what we have to do is get these formulas here ourselves. And this is how I do it. In my YouTube folder, I've got a shortcut pointing to a template. So I'm going to open up this template. I've got C1 here as a reminder. So I'm going to grab it and I just grab everything here. I'm going to right click copy. Minimize that. I'm going to go to C1 because that's my reminder of where to put my cursor. And then I want to paste. And then I want to get rid of that C1 reminder. It's put my formulas over here. And it added DX1, 2, 3, 4, and 5. And just to make things line up, I want to center that. Now usually at this point I would save it, but let me show you something. If you just click save right now, it's actually going to save it as a CSV file. Some of you may be thinking, well, no, it won't because the CSV file is read-only. Well, it's read-only because I made it read-only. To save it, you'd want to click File, Save As, Browse, Folder's highlighted, but it's still showing it type as CSV. So you're going to have to drop down and pick Excel Workbook and then give it a name. And then click Save. All right, at this point, it's now a Excel workbook. Now, I've also, as part of my template, I've added these fields to it. And the information on these fields comes from that form that I showed earlier in this video. But here I would just type in the firearm, the load, the bullet, the powder and charge weight I was using, where I was doing my testing, what was the weather, and what was the temperature. Let's take a look at the formulas I used. Well, for average, I use the Excel average function, and the range encompasses all 30 shots. If I change from that 30, I just need to change my range. Highest is just the max number Excel finds in that range. Lowest, again, it's the minimum number that Excel finds in the range. Extreme spread is just the difference between the highest and lowest velocity. And standard deviation. All right, now my version of Excel actually gives me 4 options for calculating standard deviation. So when I look it up, it gives me these 4. The one I'm using is stdev.s. That calculates the standard deviation on a sample set of data, which is what I've got. I'm not measuring every single round I've ever shot through this gun, which is the population. This is just a sample. .p is the entire population, so it's the incorrect formula to use. This one is also based on a sample, but it includes true, false, logical values and text. Well, LabRadar isn't going to put text in these fields, so it's not needed. Same thing here. This includes logical values and text, but it's for the entire population. So the one we want to use is stdev.s. Now, for those who are interested, This is the formula that the lab radar uses to calculate standard deviation. And I did some internet research, and as best as I could find, this is the formula that Excel uses for this function, the .s function. So at this point, I've got my statistics for all the distances I was interested in for all 30 shots. What I want to dive into next is the details of our velocities. If you recall, one of the things you copied over from the LabRadar unit's SD card is a subfolder called TRK for tracking. If we go into that, what you'll find is a CSV file for each and every shot you took in that series. And one might think that since we only asked for 5 distances to record velocity for, that you might find 5 velocities in here. Well, in fact, if we open up shot 10, we find that it actually recorded, and this is the velocity, and this is the distance in which that velocity was recorded, it actually recorded well over 100 velocities. The layout of this workbook is, this will be your serial number of your LabRadar unit, series number, shot number. So this is all the data just for shot number 10. This is the recorded velocity at this distance. This column is your signal to noise ratio. One thing I recommend that you do just for at least the first 1 or 2 times is highlight all the velocities except for this one. This is muzzle velocity. These numbers with an actual distance are velocities that were actually captured by the LabRadar unit. Muzzle velocity is actually predicted value. As you know, when you set up your LabRadar unit, the muzzle's right next to the radar unit. So it's actually physically impossible for it to capture the actual muzzle velocity. So this is a predicted value. So what we want to do is take your actual measured velocities. I want to highlight them and click on Insert, Chart. If it hasn't already defaulted to Line Chart, pick Line Chart. Click OK. And just take a look at it. When you look at it, this is what you'd expect. As a bullet travels over distance, it's going to decrease in velocity in a linear fashion. But down in this area, what we're seeing is a major drop in velocity, then it goes back up, then down, and then back up. So something's going on around here. This point is a velocity of 709.34, and after that it starts dropping. Well, here's 709.34, and let's take a look at what's kind of going on in this area. When you look at this, you can see that the signal to noise ratio is really dropping in value. In one conversation I had with the LabRadar people, they were telling me if the signal to noise ratio is around 12 or less, we know that the velocity number is not valid. Does this mean that the LabRadar unit is not capable of capturing velocities out to this distance, which is 54 yards, 57 yards, and so on? In this particular case, let me tell you why I think we're having trouble with these velocities. Okay, here's a picture of the range that I was shooting at. These stands right here are the 50-yard line. So as the bullet travels, goes to the 50-yard line, once it starts getting into this area, the radar is actually beginning to bounce off of sloped hills. It's covered with a lot of vegetation. And as the bullet goes into this vegetation, it's going to cause issues with tracking it. And then as the bullet hits the berm, it's going to knock up soil and rocks and possibly previous bullets. And all of those obstacles are going to cause radar signals to bounce off and come back to the unit. Well, the LabRadar unit knows it's getting these erroneous signals, and so the signal to noise ratio really starts dropping. So it isn't the LabRadar unit's fault that these velocities here can't be trusted. It's the terrain that I was shooting on. Now, does that mean my testing is invalid? Well, again, I'm only interested out to 50 yards, which is this point right here. When I look at the 50-yard numbers, I'm still getting some decent signal to noise ratios. So I suggest when you first start using the unit or you start using it at a different range, open up one of these detailed workbooks. Just run a simple line chart and see if you see the anomalies. And if you do, go look at the signal to noise ratios and try to figure out what's going on. The other thing you want to look at is your distance at the very beginning. What this is telling me is this particular shot first entered the radar signal a little over 6 yards downrange. And after that, it started capturing a velocity about every half yard. So if the bullet first entered in the radar signal at 6 yards, how do we get a muzzle velocity? Well, the LabRadar software, and I don't know the details of it, uses predictive modeling to look at these velocities, and it comes up with an algorithm that says what would the velocity be at zero distance. And I suspect that that same predictive model is used to give us these numbers. Well, the unit's not able to say, okay, has the bullet reached 50 yards? Yes. What's its velocity? That's not how radar works. Radar just keeps capturing velocities and recording the distance. Does this mean that this data cannot be trusted? The LabRadar unit collects a vast amount of data and uses that to tell us what our velocities would be at the distances that we ask for. What I want to show you next is how a very simple predictive model that I came up with, and again, I am not a statistician, can use this data to give us these types of numbers. And as a side note, this also explains why these stats that are in the CSV workbook are to decimal places. I mean, if you look down here, there is no 78107. That is because these numbers are generated off of the underlying data, which is to 2 decimal places. I don't want to spend a lot of time on this because I promised to show you a shot series where DX1 is 10 feet. But I did want to take a moment to show how a model can be used to give fairly accurate predictions given the data points created by the LabRadar. I do not know the actual model the LabRadar software uses, so I made a simple linear regression. I used all the velocities and distances except for muzzle velocity because that is not a number actually captured by the LabRadar unit. It is a number predicted by the LabRadar software. And I did not use the velocities and distances where their signal to noise ratio identified them as being unreliable. But this is the model I came up with. There actually is a regression line in here, but it's hard to see because of all the data points. This is the formula, and it's important to note that this formula is only valid for this one specific individual shot. It won't be valid for any of the other shots in the series or any other series. And this is its R-squared value. So let's just do a couple simple tests. I looked through the velocities and distances that I used, and I found the one that had the highest or best signal to noise ratio. And I also found the one that had the lowest signal to noise ratio. So what I want to do is plug in their distances, and then we can compare what the model came up with to what the actual recorded velocity is. So this one has a distance of 7.37 yards. And this is what it predicted the velocity to be, and this is the actual velocity. So the predicted velocity is 100.04% of the actual velocity. So it's off by 0.04%. And let's do the same thing for this one. This one, the distance was 50.12 yards. So this is the predicted velocity at that distance, and the prediction is 99.9% of the actual velocity. So while my model is not the one LabRadar uses, I think it is. To demonstrate the kind of accuracy we can get from predictive software, given the large amount of data points collected by the LabRadar and the very strong linear relationship between distance and velocity. Now, for the heck of it, let's just go ahead and key a distance of 0 to see what the simple model comes up with for the predicted muzzle velocity. So this model came up with a number that is 100.04% of what the LabRadar software came up with. But the point of this is to show a model can be used to come up with accurate predictions of what the velocities are for the distances we specify as DX1, 2, 3, 4, and 5, and also for muzzle velocity. Okay, at this point let's take a look at the shot series I promised you. This is the shot series where I set DX1 to 10 feet. Let's open it up. in order to get power factor calculation at 10 feet. You'd have to set your unit distances to feet and make sure that DX1 is 10. Now let's go into the details for a shot and see what the details look like. We go into tracking and let's just pick shot 1. All right, when you look at it, like the previous one, the bullet first entered in the radar signal at a little over 6 yards. And we see the predicted velocity at muzzle velocity, but we don't see anything for 10 feet. Well, the reason we don't see anything for 10 feet is because the bullet didn't enter in the radar signal at 10 feet. It was at a little over 18 feet. So what the LabRadar software does, when we ask for a distance shorter than when the bullet first enters the radar signal, it uses that predictive software that we talked about a little bit earlier and predicts this is what your velocity for each shot is going to be at 10 feet. Hopefully this gives you a better idea of the data and the metrics that the LabRadar unit gives us. This concludes this video, but if you would like to watch the other videos in the introduction series, you'll find the links here. Otherwise, I hope this video was useful to you, and thank you for watching.